Think about this for a second. Every time you turn on a light, charge your phone, or run a microwave, you're relying on a system so large and complex that most people never see it. And yet, at its core, the modern power grid is built on a few simple ideas. If you understand those ideas, electricity stops feeling mysterious. It starts feeling logical. In the next few minutes, I'm going to explain the most useful concepts for understanding the modern grid, not with heavy math, but with practical intuition. And by the end, you'll understand not just how electricity works, but why the grid works the way it does. The first concept is this: electricity is not like water sitting in a tank. The grid is more like a live balancing act. Power plants generate electricity, and homes and businesses use it almost immediately. The grid has to match supply and demand in real time, every second of every day. Why does that matter? Because electricity is hard to store in huge amounts. So if demand suddenly spikes, like when millions of people turn on air conditioners during a heat wave, the grid has to respond instantly. That's why grid operators care so much about forecasting. They're not just guessing tomorrow's usage. They're planning the exact amount of power needed at different times of day. Concrete example: imagine a football game ending and everyone getting home and making dinner at the same time. That spike in demand is real, and the grid has to absorb it without collapsing. Here's the next useful idea: electricity moves through wires because of voltage. Voltage is like electrical pressure. Current is the flow, and resistance is what slows that flow down. Now here's the important part: we use very high voltage to send power long distances because it reduces energy loss. Why? Because when current is high, wires heat up and waste energy. By increasing voltage, the grid can deliver the same amount of power with less current, which means less loss. That's why you'll see big transmission lines carrying electricity across regions. It's not because they're stronger in a dramatic sense, it's because high voltage is efficient. Useful takeaway: if you ever wonder why power lines are so tall and massive, it's because they're moving large amounts of energy efficiently over long distances. So how do we go from huge transmission voltage to the smaller voltage your home can actually use? Transformers. A transformer changes voltage up or down using magnetism. It doesn't create energy. It simply moves it between different voltage levels very efficiently. This is one of the most important inventions in the history of electricity. At power plants, transformers step voltage up for transmission. Near cities and neighborhoods, transformers step it back down for safe use in homes and businesses. Concrete example: that boxy device on a utility pole or in a neighborhood electrical cabinet? That's often a transformer doing the final step down before electricity reaches your house. Without transformers, the modern grid would be far less efficient and far more expensive. Most of the modern grid uses alternating current, or AC. In AC, the direction of current reverses back and forth many times per second. In many countries, that happens 50 or 60 times per second, depending on the system. Why use AC instead of direct current or DC? Historically, AC made it much easier to change voltage with transformers. That made long-distance transmission practical and cheap. Today, DC is also used in some places, especially for very long transmission lines and some renewable systems. But AC still dominates most of the grid because the infrastructure is already built around it. Useful idea: the grid is not one single technology. It's a layered system that uses different methods where they make sense. Now here's one of the most fascinating concepts: frequency. In an AC system, the electricity oscillates at a fixed frequency, usually 50 or 60 hertz. That frequency is like the pulse of the grid. Why does it matter? Because if generation and demand get out of balance, the frequency can drift. If too much electricity is being consumed and not enough is being produced, the frequency can drop. If too much is being produced, it can rise. Grid operators watch frequency very closely because it's one of the fastest indicators of trouble. Concrete example: if a major power plant suddenly goes offline, the frequency can begin to change almost immediately. The grid then needs backup generation or automatic controls to stabilize it. This is why electricity isn't just on or off. It's a dynamic system with feedback. Another important concept is redundancy. The grid is built so that if one line, transformer, or generator fails, the system doesn't immediately collapse. This is essential because failures happen, storms hit, equipment breaks, fires happen, demand changes. So the modern grid is designed with backups, rerouting, and reserve capacity. Useful example: if one transmission line is overloaded or damaged, power can often be rerouted through another path. That flexibility is part of what makes the grid resilient, but it also makes it complicated to manage. All of this becomes even more important as the grid changes. Solar and wind are growing fast, but they don't produce power on command the way traditional plants often can. That means the grid needs better forecasting, more storage, stronger transmission, and smarter controls. Battery storage helps because it can absorb extra power when supply is high and release it when demand is high. Long-distance transmission helps because wind and solar resources are often far from the cities that need them. And smarter grid control systems help manage all of this in real time. So when people talk about the future of electricity, they're really talking about making the same basic grid concepts work in a more flexible, more distributed world. The modern grid can seem invisible, but it's one of the most impressive systems humans have ever built. And once you understand a few core ideas, balancing supply and demand, voltage and current, transformers, AC frequency, and redundancy, you start seeing the whole system differently. Electricity isn't magic. It's coordination. And the grid is where physics, engineering, and human civilization all meet. Electricity explained simply, the most useful concepts for understanding the modern grid is just one small part of how electricity works: power circuits and the grid. If you're interested, our full free How Electricity Works, Power Circuits and the Grid course is linked in the description. It includes more than 100 subtopics.